All right, by this point, we've gotten more comfortable with traits and we've talked about structs and we've talked about enums, iterators, collections, quite a lot of stuff in Rust actually. But we haven't really talked about pointers yet. And pointers are, I think, is a topic that came up once or twice before, but we jumped over it simply because it wasn't really time to talk about them then. So let's dig into pointers in this section of the video. So in order to understand pointers and how they work, you need to understand heap versus stack. Is a topic that I mentioned quite a while ago, actually, in this course. But let's think about it one more time. Stack is a last in, first out kind of a memory that's available to every function and also to your entire application. It's memory that is allocated by default to your function. So once you're in a function, you can create stack values, for instance, integers and floating point values. And those values are local to your function. Once your function is done, those values are also gone. But a lot of people think that those values get deallocated, but the truth is that these values get pushed into the stack and then popped out. And the process of popping a value from the stack doesn't necessarily mean that you're actually deallocating that object. Simply means that the stack pointer, if you know assembly, and the base pointer are changing their position. For instance, actually not the base pointer, stack pointer is popping to a different position in the stack, to a higher position, kind of concealing the value in the stack, but that value is still in the stack. However, when your function returns to its caller function, then the base pointer is at a different place, meaning that basically that function and its stack are kind of gone. Though the stack is still available, it's a memory that is available to your entire application, but the caller is never going to do something shady and go and access another function's stack space, so to say. Okay, especially when you're using high-level languages such as Rust. But if you're working with, assembly, you can do some really shady stuff with that. However, heap is random access, so you can ask your operating system to allocate some heap memory for you, and you can basically store values in the heap as you want to. So it's quite different from the stack. Okay, now let's talk about the first pointer in Rust, and that is called a box. And a box is a data type that stores values for you in the heap. So even if your value is such as is like an integer, that integer will be able to be stored in the heap and not the stack using a box. Okay, so let's go ahead and see an example of a box. So if I go in here and say age is a box new, and let's say 22 in here. Now this you can see it's a box of I32 in here, and box is a generic struct, as you can see in here. Okay, so what you can do then is, as soon as you have that age, you can actually return or extract the value inside that box. And let's say twice is a pointer to that box basically, and multiplied by 2. So you're dereferencing your pointer of type box in here and multiplying its value, which is stored in here, by 2. So this is how you would basically reference the value which is stored inside a box. And you can print that to the screen, as you can see in here. Twice is going to then be 44 in here stored. Okay, so box is used for storing values in the heap, whereas the value itself could essentially be in the stack otherwise. Okay, so in some cases, while you're doing Rust development, you may want to store stack values inside the heap, and that's where you would use a box for. Okay, now if you look at the box source code in here, and we look at a deref in here, let's see, you can see that this is a deref implementation on box. Now, what is deref really? Deref is a way for Rust to dereference the value inside a box. It's a little bit strange, but it's kind of like you pointing indirectly to a value that is inside the box. Okay, now, in order to understand how this actually works, let's implement our own box. And this is something that's recommended by Rust's documentation itself, that you implement your own box to see how box actually works by its default implementation. So let's go ahead and create our own box, and we're going to call it BoxedValue in here, which is structure. So BoxedValue, and this can store any value of type T in here, and our value is T, as you can see in here. Okay, so this is a simple struct that stores any value of any type, pretty much. Okay, now let's go ahead and create an implementation block for our box value. So impl t for boxed value in here. Okay, oops, not for, t like this. And then we're going to say fn new. Actually, that was pretty nice. This is exactly what I wanted to implement. So this creates a, we can return self in here. So this should also work, I believe. Okay, so you can see that we have a new function in here, which is not an instance method, but it's actually just a method working on boxed value. Takes a value and returns a boxed value as its result. Okay, so let's go ahead and create an instance of this. So we say boxed value in here, okay, and just leave it like that. And this code should compile without a problem. Now, let's go ahead and try to dereference the age. So you saw in here, we had this twice, which was dereferencing the age, okay? And we were multiplying by 2. So let's go ahead and say value here. Let's say value is, and then we print the value, and then we dereference the age, okay? As you can see in here, okay? Or, yeah, like that. So that's fine. So you can see now we will get an error in here saying cannot be dereferenced. And this is basically why we had that deref implementation on box. So if we go ahead and implement the deref trait for our box value as well, then we can have Rust read the value of our box value just like it does for box as well. So let's say impl t deref for box value of t. And let's see in here then, okay? And let's see what deref, cannot find trait deref, okay? And because this is std ops deref, I think that should be actually it. Good. Okay, so we had to use std ops deref in here. So please make sure that you import std ops deref first, and then we're going to implement deref for our box value. And as you can see, first we have to specify our target in here. Okay, so what kind of a value we're returning, and the value is of type t. And then you implement the deref function itself, which returns that target, and that target is our self value, basically. So after implementing deref for box value, then you are able to get Rust to print the dereferenced value, which is stored inside our boxed value. So if you go to the terminal, you can see now the value is 22 being printed to the console. So that's what dereferencing does. It reads a pointer or a box value's actual internal value. Okay, so the value that is stored in the box itself. Okay, now you can also dereference the value yourself. So you can say actual age is age deref, okay? And then you can print it to the console. You can see then it is printing 22 as well. So this deref is a function that is coming from implementing the deref trait on your actual box value structure. So you saw earlier that you can see now this is a reference to an i32, and in here by saying actual age is age pointer as well, then you're actually getting an i32 back. So deref points to it, kind of like calling the deref function, it gives you a reference to the actual value, and doing this asterisk in here and your box value gives you the actual value that comes out of your box value. Okay. So there's basically a difference in there. You know that already by this point. Now, you can point to the underlying value, as I mentioned, using this asterisk in here. Okay, but this may not be always the thing that you want to do. Maybe you actually want to get a reference to that value, and then you can use deref for that. Okay. Now, so this when you get a pointer okay, so let me just write these for us in here. We say actual value, and then we say let ptr to value or ref to value, okay? And then we say it is equal to age deref. So you can see the data types in here, how they differ from each other. One is an i32, the other one is like a reference to an i32. However, you can also write a pointer to your age deref. So, and we say let other, okay? So you can see in here, by saying pointer to an age deref, then you're getting your actual value out. And that is pretty much what this asterisk is doing for us. So if you see the syntax of asterisk a box or a box value, something that conforms to the deref trait, you know that you're getting basically a shorthand. It is pretty much a shorthand for asterisk age deref, okay, or asterisk variable deref. So it's calling the deref function on that object and is pointing to that dereferenced value, okay? So there is something called an implicit deref coercion in functions, and Rust helps with that. And it's very similar to what is happening in here. What is going to happen is that Rust is going to automatically help us dereference a value that is passed to a function. So let's have a look at an example. Let's go ahead and create a function in here. As you can see, it's called print integer, fn print integer. Okay, and this takes an I32 reference. Okay, and all it does is just prints it to the screen. Okay, now let's go ahead and create a new box value in here. So I'm going to remove all that code, and let's say let value is a box value of 10 in here. Okay, so what we're going to do then is to pass it to the function using an ampersand. So you can see that you may in your head be thinking, oh, but wait a minute, if we pass this with an ampersand to this function, it's going to become an ampersand of box value. So it's going to be a reference to a box value. But if you do a test in here, for instance, and say ampersand value, and look at the data type, you can see that, oh yeah, it is an ampersand of box value, but how can we pass that to this function? So let's have a look at an example then. We say print integer ampersand value, and you would see then, oh, it compiles completely fine. And that is what is called an implicit deref coercion in Rust. What is happening in here is that Rust understands that what you expect in here is a a reference to an I32. And by creating a reference to your box value is actually extracting a reference to, or is calling the deref on this for you, and extracting a reference to the value which is stored inside the box value into this function automatically for you, instead of you having to do all the deref work manually. Okay, so that's short and good about box and box values. You can read a lot more about them in the documentations. And unfortunately, I can't go into too much details about all these pointers, because otherwise this video itself about pointers will be quite a few hours long. So let's talk about RC, which is another pointer type in Rust, and RC stands for reference counted. And some other programming languages, such as Objective-C, actually have reference counting, and it's available also in Rust, but not at its core. But RC is available for those of you who are interested in reference count pointers. Okay, so let's see how it actually works. Let's import stdrc in here. So let me remove all this code that we've written up to this point. So let's say use stdrc RC in here for reference counting. Okay, so now that we have that, we can go ahead and experiment with it. Now, RC, as you can see at the bottom of the screen, this allows mutation of the wrapped values. So RC is just basically a reference counted, basically a reference to a value that you can increment the reference and decrement the reference. So Rust keeps track of how many times you've incremented the reference and how many times you need to decrement the reference. Okay, but you can't mutate the value inside your RC. RC is also single threaded. It is not meant to be passed. It's not meant to be created in one thread and passed into another thread for any type of operation. So if you're looking at multi-threaded environments, RC is usually not a good choice, but there are some ways of actually going around that as well. You can create weak references to RC, which is reference counted pointer, and weak references generally don't own their data. They just get a weak reference. So it's just, as long as that object exists, then your weak reference also available. But as soon as that RC drops its reference count and like drops the object that it owns, then your weak reference also is not going to be valid, but your application is going to crash. Okay, and this is kind of like unsafe Rust coding. Let's have a look at that. Let's create an array in here. So we're going to say let array, and we're going to call create a vector in here, and let's say John toString. And then we're going to also add Jane toString in here. So we have a vector of string objects created in our application now. Okay. Now let's create a reference count to our array. So let's say let RC is RC new This is how you would create a new reference a new reference to your array. Now, if you want to get an unknown kind of, or you want to get a weak reference to this RC, then you would create a downgraded RC out of this. So you would say let weak reference, and then you would say RC down. Oh, this is actually exactly the code I want to write. RC downgrade, and then you pass a reference to your RC. Okay, so you can see now you have a weak reference to that vector. What this really means is that as soon as your RC drops this value, which is this array, then your weak reference won't be able to access that array. And we're going to see an example of that now. So let's go ahead and drop that original RC, which then drops the value that this RC refers to. So with the drop function, okay? And we say we want to drop this RC, okay? So now we've done that. Now we have a weak reference in here. Now, if you want to access this weak, then you have to upgrade it, because you saw that we did a downgrade, but you want to access its value, then you have to do an upgrade on it. So we say upgrade to grab the value in here, and then we want to unwrap it, okay? Because if you just do an upgrade, let's see, let's test is weak upgrade. You can see the data type in here is an option. So now we expect that option to be there. So we say unwrap it. If you remember from the option chapter when we talked about optionals. So we say let value, and then we print the value, okay? So value. And now we're going to get a panic in the terminal, as you can see in here. And it says called unwrap on a non-value. So what happened in here was that RC is actually this weak pointer. By calling upgrade on it, is returning an optional to us. Basically it's not holding onto the value after it has been dropped. So if you want to work with reference counting and weak references, then RC is the one for you. But if you're going to pass it between different threads, then that's a completely different story. So I'm not going to go too much into weak references and how they work. You can read more about them by just Googling them, because then this video will be very long. But just know that weak references are useful for when you don't want to really have anything to do with an object that someone else owns. You just want to get a reference to it, and if that object exists, then you can use it. If it doesn't exist, you don't worry about it at all. So that's when weak references are useful. So we saw that upgrade returns an optional. That means that you can actually do match on it. So we can say match this weak upgrade, and then we can then get the sum and none arms in here. So you can see in terminal, now we're going to get none printed to the screen because we did a drop on our RC. But if we don't do a drop on our RC, we can actually get the values, which are John and Jane. Okay, so that's how weak references work with RCs. Now, if you want to create a new RC, so if you have, for instance, this array, and then you have RC created in here, which is a reference count to that, and if you want to create a new instance of that RC, then you can do a clone on it. So you say let RC2 is rc.clone. Okay, so this basically creates a completely new RC, and the array is completely created from scratch. It's kind of like cloned as well. Now, you can also create this clone. Actually, before I go there, let's see an example of dropping the RC, but you still have access to your RC2 in here. Let's see in here. You can see John and Jane are still available in RC2 because RC2 is a clone of your original RC, okay? Now, instead of doing RC clone in here, you can also do RC clone, and then you can pass a reference to your original RC in here to do the cloning. But I personally prefer RC clone in here because this clone is also a function that's available on every instance of an RC. Okay, so if you want to mutate values that are stored inside an RC, well, you're out of luck. That is not allowed with RC. But there's another type which is called cell in Rust, which does allow mutability, and we can have a look at that right now. So let's delete this code in here, and let's go and import std cell in here, okay? And then we're going to go create a person struct with a name and age. And so let's say person struct person, and its name, and we say it's a string, and its age is going to be a cell of let's say U8 instead of U32. So The cell is kind of a pointer that allows internal mutability. And I've always said that it's kind of dangerous. So you have to be kind of careful when you're using cell because it allows mutability even when the type itself doesn't appear mutable. Okay. So let's go ahead and add a function to our person that allows us to increment the age. So let's say impl person, and let's say fn increment age, okay, and then get a reference to self in here. And you can see this function doesn't seem like it's mutating self because self is not passed as mutable in here. But what it can do is, as you can see at the bottom of the screen, you can say self age, and then you can call a set function on it, and then you would say self age dot get +1. So you're pretty much just mutating that age by using this function. Okay, let's go ahead and create a new instance of person in here. So let's say let person is, let's see if GitHub Copilot can help us with that. So you create a cell new with the age of 20, okay, and we can go ahead then and get the new age by calling the increment. So let's say did we actually return from increment age? It seems like we're actually returning the value as well. So in the previous stage, we were supposed to return the U8 as well. So let's just return self age dot get. Okay. So we return the new age in here. Let's say new age is person dot increment age, as you can see in here. Okay. And let's see what happened. And then we can print ln this new age to the console. You can see new age is then going to be 21. If you can find that, 21. All right. And that means that the person's age is also now 21. So if we read this, let person age is person age get, and let's print both of them, person age and the new age. They both are going to be 21 in this case. You can find them. So you saw in here, this increment age appears very innocent in that it doesn't take a mutable reference to self, but is internally actually mutating that reference. So this is the power of using cell pointers in Rust. Now, cell allows interior mutability, and it's considered to be unsafe in the Rust world. So you kind of need to avoid it unless you really need that. So if you need cell, you have to have a compelling reason actually for why you've moved on to cell. Sorry. So if you basically, if you are considering using cell, it's best that you have a look at the reasons that you have and see if really cell is what you want, because cell, as I mentioned, is considered unsafe. Now, if you're kind of having a look at cell and kind of scared of it, there's another pointer in Rust called RefCell, and it's for multiple immutable borrows or one mutable. So you can have multiple immutable borrows of the same value that's stored in that pointer, and if you have then mutability, then you can't have immutable borrows. So it's kind of like a more safer version, or more safer is a safer version of using cell. So this is called a RefCell, and the mutability and immutability rules of RefCell are enforced at runtime and not at compile time. So you may get panics at runtime if you're doing things wrong, as we're going to see an example of that soon. Now, RefCell is only allowed in single-threaded environments, and in this case, it's similar to cell and RC. So if you're working with multi-threaded environments, then there are other ways of solving your pointer needs than using RefCell, for instance. So RefCell can be borrowed immutable or mutably. As you can see, you can say your RefCell borrow or RefCell borrow mutably, but you just have to keep in mind the rules of RefCell that I mentioned. So you either have one mutable borrow or you have multiple immutable borrows. Okay, so let's have a look at creating a RefCell in here. So we have our person. Let's see if we need that at all. Maybe we don't need that, so let's just remove that for now. And I'm going to remove the implementation for all of this. std cell, okay. So let's see if we can create a RefCell in here. So let's say RefCell, let RefCell is a RefCell new. Okay, and in here we create a vector and we say 1, 2, 3. Good stuff. Okay, and we have to import RefCell, std RefCell. Good stuff. Okay, so this is the creation of a RefCell. It's very easy. Let's go ahead and get a mutable reference to this RefCell. So we say let mutable mutref. Okay, so we basically say it's mutable, and then we say RefCell, and then we say borrow mut, like borrow it mutably. So you can see now you have a ref mutable of that vector of I32. Okay. Now, if you get an immutable reference to the same vector, then you say, for instance, len is RefCell, or what do we call it? RefCell, I believe. Yeah. And then you borrow it immutably, okay? And then you get the length of that. So if you just borrowed it immutably, you would get your reference like this, and then you would say len in here. Okay, so let's get the length, and then we can print it out to the console if you want to. But before doing that, let's go ahead actually to the next stage. And using the mutable reference now, since we have that, we're going to push a new value to that vector. So let's go in here and say we push a value of 100 in here. But remember, we had a bit of a rule before that you can either have one mutable borrow to your RefCell or multiple immutable borrows. But in here, we mix and match. We have one mutable borrow, and we have also an immutable borrow, and this is not a good idea. So let's go ahead and print the length now. So let's say print ln length is length, like that. This is good. And have a look at the terminal. So and you can see the panic at runtime is telling you already mutably borrowed, and this is that rule that we've now mentioned twice. Now there are ways to combine pointers, and we're gonna see examples of how to use pointers. The concept of pointers are kind of like abstract in pretty much every programming language. In C is a little bit easier to understand. C++ is a little more difficult. And in Rust, pointers are a completely different monster because Rust tries to add memory management to pointers at a completely new level, which isn't even available in C++. So if you want to get more comfortable with pointers, I suggest that you have a look at Box, you look at Cell, and you look at RefCell as well. I think these three are kind of like the most important ones to understand. And you can do some more experiments on your own as well to get a better understanding of pointers. Now, learning pointers in Rust, in my opinion, at least, is a must because you pretty much can't write any professional application with Rust if you're not comfortable with pointers. So grab a cup of coffee, do some experiments of your own as well, and have a look at the code that we've written in this chapter. And I hope that you get a better understanding of pointers by the end of that. So that's about that for this chapter of the video, and I'll see you in the next video.